Hello, welcome back. The title of this lesson is called Newton's Second Law of Motion, and this is part 1. So this is, without a doubt, one of the most important lessons you'll ever watch and learn about in physics. There's an old joke that if you know Newton's second law of motion, you can solve almost any physics problem. It really is that essential. When we talk about frictional forces and motion through space and spacecraft, and even later on electromagnetic forces, anything involving a force, when you want to figure out how that force influences something to move, Newton's second law of motion, it comes into play. So, no pressure here, but it is that important. I encourage you to watch this a few times. Now, the good news is I'm going to explain it to you in a way that you'll understand it in your bones. You'll know what Newton's law actually is, hopefully give you some additional insights along the way that maybe you won't get out of a standard textbook somewhere. Now, remember, the number one thing we talked about in Newton's first law of motion, as I tried to beat it into your head, that forces do not cause motion. In other words, objects move in deep space in a straight line without any force. What actually happens is forces cause motion to change. So if an object's at rest and I push it, it changes its motion, it starts moving. If an object is already moving in a straight line and I push on it, then I change its motion to speed up or slow down or to change directions. So forces actually cause an object to change its motion. But what is a change in motion? A change in motion is an acceleration. So what we're saying is that forces cause acceleration. That's what we learned before. Forces cause acceleration. Newton's second law of motion, it writes this down in a mathematical way. So let's talk about it. Newton's second law of motion. The first law of motion was more of like an object at rest tends to stay in rest, an object in motion tends to stay in motion unless you push on it with a force. Newton's second law is the following. The force that you apply to an object is a vector quantity, and it's equal to the mass of the object multiplied by the acceleration that the object has. F equals ma. Now I'm putting the vector arrowheads on top to remind you that the force is a vector, it has a direction, and the acceleration is also a vector, it has a direction. The mass of an object is just how many kilograms it has, so there's no vector associated with the mass, okay? Now before we actually talk about this, let's write down the units of this thing. Now the force that we're talking about is always measured in newtons. The mass of the object is always measured in kilograms, not grams, kilograms, and the acceleration is measured in meters per second squared, right? And that's very, very important. So whenever you are calculating something in terms of forces and accelerations and things like that, keep your accelerations in meters per second squared. Keep your masses in kilograms. If you have some other unit like grams, change them into kilograms. And when you do that, then the forces will always be in newtons, right? And remember, a newton, as we talked about before, is roughly the force that you will feel from an average apple. When you hold an apple in your hand, that's about a newton. It's pretty close to a quarter of a pound if you like using pounds, but of course I don't like using pounds, but some people need that in the beginning. It's about the force you feel in an earth gravity of an apple sitting in your hand, a typical medium apple. What does this equation mean? This means that if I know how much something is accelerating, I can measure its acceleration. And I know how much mass that object contains. By multiplying these two, it tells me how much force I must be pushing with to cause that acceleration. Because remember, things only accelerate when there's some sort of force somewhere. Only. I'll say it again. Things only accelerate. They don't accelerate for no reason. You have to have a force. Newton's first law says things want to move in a straight line at a constant velocity. That's no acceleration. If I go into deep space and throw something, it's going to go forever and ever and ever in a straight line with no force applied. No forces. It's just coasting, right? But if I want to accelerate that object, what Newton's second law is telling you, if I want to speed that thing up, I have to apply a force to it. And that force, which is a pushing force of the rocket engines, is going to be equal to whatever the mass of the object is multiplied by whatever acceleration I want to give it. If I want to speed that thing up, let's say 5 meters per second squared, that's the acceleration. Then I multiply by the mass and it tells me how many newtons my rocket thruster must push with. So what it does is it relates the pushing of things, or the pulling, the forces, with how does the object respond. Because remember, forces don't cause motion. Motion happens automatically in a straight line forever and ever. Forces cause the motion to change, which is what we call acceleration. Now, that is what you're going to get out of most lessons, most lectures, most books, and I'm not trying to say that I'm like some brilliant person telling you stuff that other books won't have, but what I'm trying to do is I want to focus on what I think things that aren't emphasized as much, because anybody can take this equation and multiply two numbers together, and we could do our first problem like right now. But I want to go deeper, because I want you to understand a little subsurface, a little bit deeper layer as to what's happening here. All right? Force is equal to mass times acceleration. What it means is that in order to produce an acceleration on some mass, I must push with some force. Alternatively, if I apply a force to some object and I know its mass, then I can calculate the acceleration that will result from that force of pushing or pulling. All right? Now, the vectors that are on top of these things, this is what we call a vector equation. And what it means is that because they're vectors, remember, a vector is a number, a magnitude, and also a direction. And because the acceleration has a vector and the force has a vector, both sides of the equal sign, what it means is that the force must be in the same direction as the acceleration. That makes sense. If there's an object here in space and I push this direction, I expect it to accelerate in the same direction. The vector arrowheads mean that the force and the acceleration always have to be in the same direction. Always. That little nugget right there will save you a lot of time in many problems, because sometimes you're not sure which way the acceleration should go, but you'll have some forces, and then you remember, oh wait, Jason said the force and the acceleration, they always have to be in the same direction. Why? Because this is an equal sign. And that means that the multiplication has to equal to the number of newtons, sure, but the direction over here has to be the same as the direction here, because this is a vector equation. So now we're growing up a little bit, right? In like 6th grade, you learn how to write an equation. Y equals 3x plus 4. That's just an equation with numbers. Put numbers in, and you have to have the same numbers on both sides. But now we're growing up a little bit. We're in physics. And now we have a vector equation. And that means that the numbers you multiply have to equal the force. But since it's a vector, the direction here has to be the direction of the force. That's what the vector arrowheads on both sides mean. Because when I first learned physics, I kind of ignored the vector arrowheads. I didn't even write them half the time because I didn't care. I just thought, well, I'm calculating the force. But it's very important to know that the force and the acceleration are lined up. So what does this mean? Let's take a couple of examples, because this is just a general equation. But now let's say that I give you a force which exists only in the x direction. Then what it means is it's equal to the mass times the acceleration, which happens in the x direction. So this is a component in the x direction of the Newton's second law. And we also now know that the force which is pushing in the y direction is equal to the mass times the acceleration that happens in the y direction. Now you see how we're starting to break it into components. We learned in the past that we can break forces into x and y components. Why? Because then we can treat the x component as its own equation, find the acceleration in the x direction. We can use the force that's in the y direction component and get the y version, or the y amount of the acceleration. So to draw a few pictures here, let's say we have some block with a mass m. And this is the x direction here. So let's say I push to the right in the x direction. This is now purely in the x direction. I push on some box of mass m, and it's going to produce some acceleration in the x direction. The force and the acceleration are in the same direction, right? What happens if I have a block and I push upward in the y direction? Well, what it's telling me is that the acceleration is the acceleration a sub y is going to happen in the y direction. So the force is equal to mass times acceleration exists in the y direction, and the force and the acceleration are lined up in the same direction. The force and the acceleration in the x direction are lined up in the same way. So if you now broaden yourself and say, well, what happens if I'm not pushing in the x or the y direction? Let's say I'm pushing on this corner at some angle, and now I'm not going to put x or y here because it's just some vector. some oblique direction. It's not really purely in x or purely in y. But what you do know is that the force and the acceleration have to be lined up. So these two vectors are lined up in the same direction. When you read force is equal to mass times acceleration with vector arrowheads, it means the directions are the same too. Now, in real life, if I was pushing on this block with some force at some angle, I would break this force into a vertical and a horizontal component. And then I would calculate the vertical and the horizontal component of the acceleration, which would reproduce what is happening here. But still, I just want to show you the force and the acceleration in all of these cases are in the same direction. So now let me get a little philosophical and tell you some insights that you may or may not read in a book. You can see that force is equal to mass times acceleration. We now know that force and acceleration are both vectors. They're both in the same direction in all of our pictures, but the length of the arrows might be different because, of course, when I multiply these, I'm going to get a new number over here, and so the length of the arrow might be bigger or smaller for force, but the directions will be the same. So basically, the force is a vector arrow in one direction. The acceleration is a vector arrow in the same direction. The only difference between the two vectors, other than what they represent, is the length of the arrow. So what you can say is that the force in this equation and the acceleration in this equation, they're basically related to each other by a conversion factor. The conversion factor is what we call the mass of the object, right? So the mass here, it's telling us how much influence the force has to produce an acceleration. In other words, remember the concept of inertia. We said we go into deep space and we have a very massive object like a car, like an automobile. If we push on it with 1 Newton, it's going to move, but it's not going to accelerate very much because it has a high inertia, right? So if I have a very high number here and I push with the same force, then I'm not going to get very much acceleration. If you think about dividing by m, if m is very big, I'm dividing by m, acceleration is very, very low. And if I go to a golf ball, which has a very low mass, and I push on it, it's going to accelerate rapidly. So the mass is the conversion factor. That's, if you think about a conversion factor, what I mean is, like, you know that there are 100 centimeters in a meter. It's a conversion factor. Meters and centimeters are sort of the same thing, but the 100 is a conversion factor to change one into the other. Or liters to milliliters. Or, you know, I can pick any unit I want to. I can pick a unit of density if I want to. All right? But you're converting between one unit of measure and another. So instead of thinking of forces as like a totally different thing as accelerations, philosophically, you can think of force and acceleration being the same thing. They're both vectors. They're both pointed in the same direction. They just have a different scale factor, and that scale factor comes about because of the mass. The mass tells us how much influence that force has to produce a change in motion. I'll say that again. The mass is a conversion factor that converts from forces to accelerations. And it sort of behaves as a conversion factor that tells us how much influence the force actually has to produce motion. If I have a very high mass, then a force will not produce much motion. But if I have a very low mass, the force will produce a lot of, I say motion, a lot of acceleration. So that's a little philosophy, but I mean, it's basically what's going on here. These two things are the same direction. That's the critical thing. The mass behaves almost like a conversion factor. Now, it's very important for you to realize that when I say force is equal to mass times acceleration, it's really the net force acting on an object. So let's say, for instance, that I have a body with mass m, and I have lots of forces acting on it. So I have a force like acting right here, I have a force acting here, a force acting here, and like, I don't know, it could even be pulling, some force acting right there. Maybe some force acting right here. So you could do a couple of different things. You could apply each of these forces equal to mass and find out the resulting acceleration separately due to each of these forces. Then you would have all of these different acceleration vectors, and you would have to add the vectors vectorially, and you could get the answer. But what we actually do is we change the problem from all of these different acceleration forces acting on the object. What we really do is we find the vector sum of those forces. And let's just say in this problem, once we add all these vectors up, we do the head to tail and we draw and all that stuff, we figure out that really the force resolves to being something like this. So the sum, this is sigma here, the sum of the forces, or you could call it F sub net. We call it the net force. The net force is what happens when you add vectorially all of these forces together. It behaves as a single force acting here with this amount, right? Then the acceleration, of course, has to be in the same direction as whatever the net force is. So when we say force is equal to mass times acceleration, if we have multiple forces, we resolve it to a single force, and then, of course, it's equal to mass times acceleration. We get a single acceleration out of it. So the way you might see that written in a book is really that the sum of these forces is equal to the mass times acceleration. This is a better version of Newton's laws because what you do is you add up all the forces, and the resultant force, but you're adding them vectorially, the resultant force is what matters to produce the acceleration. Another way you might see it is you might see it as F net is equal to ma, right? The net force. So what I'm trying to say is when you have multiple forces acting, you resolve it to a single force, and that single force behaves equal to mass time, and you can produce that acceleration there. All right? Now, what does it actually mean graphically? I'll do a couple of different things. I'm going to draw some pictures. But what I'll use is my magnet here. Let's say I'm producing a force. This is kind of more like this going here. I'm pushing here. And as the thing starts moving, my force is still being applied. You can imagine it being like a rocket thruster attached to the object. So as I move it, I'm still pushing it. Then it goes faster and faster and faster. I'll go over here. Because the force is still in contact with the object, well, if I can hold it, it goes faster and faster and faster. Because as the thing is moving, the force is still being applied. As long as the force is being applied, the acceleration is still happening, right? So if I continue applying the force throughout the entire time, it's accelerating the whole time. But let's say that I accelerate a little ways, and then I just let go of the force, and then the thing is going to go coasting in a constant state of motion. So if you have a rocket thruster firing, I'm accelerating the whole time, but then when the rocket cuts off, I'm coasting at a constant velocity. And everything starts floating in deep space because I'm at a constant velocity, an inertial frame of motion. So graphically, I can draw this, and I can say, here's an object with mass m, and I'm going to apply a constant force to it, and then I'm going to have some velocity. So I'm going to put a force right here. Now, at some snapshot in time later, I'm applying exactly the same force. Well, what's going to happen? The velocity is going to be bigger than it was. Because force is equal to mass times acceleration, that means that there is an acceleration happening, so the velocity must be getting bigger. So the acceleration is an arrow represented right here. The arrow for the acceleration is the same length, but acceleration is making the velocity bigger the whole time. That's what it's basically doing. And then if I go here and do the same thing, I'm still applying my force to the same mass, but now, because I'm still applying that force, that velocity is even bigger, again, in the same way, and then I have an acceleration there. So acceleration is a vector. I need to put my vector arrowheads on these. You see, the acceleration vector is the same, because an acceleration is meters per second squared. That's meters per second per second. That means every second that goes by, I'm adding a certain number of meters per second to the object. And so every second that goes by, the velocity arrow gets bigger by the same amount. All right? Now let's do the same exact thing, but I'll turn it around and I'll change the direction of the forces. Let's say I start right here. Initially, my velocity is going this way. Right? There's my mass. And what I'm going to do now is I'm going to be firing a thruster in this direction. So now, you see, whereas these were lined up, here my force is actually going contrary to the velocity. It's not trying to make it bigger, it's trying to make it smaller. So what's going to happen in the next instant of time? The force is the exact same thing, the mass is the exact same thing, but what's going to happen is the velocity, I think what I'll do is I'll make this initial one a little bit longer. Then what's going to happen is in the next instant of time, the velocity is now smaller, because the force is fighting the direction of motion, and basically it's slowing it down, making this arrow now smaller. So it's slowing down right here, right? And then when I get to this point right here, I'm going to have a mass. I'm going to have the same force right here, right? But what's going to happen is it's going to slow down, and then it's going to start accelerating. Well, it's accelerating the same, but it's basically going to slow down, and then it's going to start to go this way. And so I guess I'll change it to probably red. Then I'm going to have a small velocity in this direction, right? And then looking at this and then projecting forward, if I have the same force right here, What's going to happen another instant in time right here is the velocity is going to be bigger in this direction. So you see what's going on. When the force runs counter to the velocity, it slows it down, and then it basically goes like this, and it goes this way. But see, that's always an acceleration in this direction. I'm still accelerating in this direction. The A arrow is the same. Because what's happening, force, velocity and acceleration are different. So I'm subtracting velocity, and now I'm still subtracting, so I'm still making it bigger in this direction. So force and acceleration are acting in the same direction. You might say, well, wait a minute, you always told me that force and acceleration are acting in exactly the same direction. The arrows are in the same direction. Arrows are in the same direction between force and acceleration, but here the arrows are different directions, right? But actually, when you look at it, the force is right here, and the acceleration is acting in this way. The force is right here, the acceleration is acting in the same exact direction in all cases. So the velocity and the acceleration don't have to line up, but eventually the thing will slow down, and if it's accelerating the whole time, it'll scoot back the other direction. These pictures are just intended to give you an idea of how force and acceleration and velocity all behave with respect to one another. And now we want to go back and talk about a little bit more about the definition of what a newton is. I told you in the beginning that a newton is basically the force you feel in your hand from a medium-sized apple. It's pretty close to 1/4 of a pound. It's not exactly 1/4 pound, but it's pretty close to that. Feel an apple on Earth's gravity, that's what it feels like. Let's go and talk a little more detail about this. Now that we know that F is equal to ma, right? Now that we know this, then what we know is that if we know that 1 is equal to 1 times 1, right? So if we have 1 newton right here, that's going to be the same thing as 1 kilogram accelerating at 1 meters per second squared. You see 1 is equal to 1 times 1, and these are the correct units in there. So what this is saying is that 1 newton is the force that is required to take 1 kilogram of mass and accelerate it by 1 meter per second squared. So this is something you can figure out in a lab. You could take 1 kilogram of mass, you can push it with a certain amount of force and measure the resulting motion, and when it accelerates exactly 1 meter per second squared, that is the force that you're pushing on it. It has to be exactly 1 newton, and that works out to be the amount of force you feel in your hand from, an apple. All right, let's jump into our first problem and get some practice actually calculating this. The first problem says, the 32.50 kilogram space probe is being subjected to a constant force of 140.0 newtons from a ship's tractor beam after initially being stationary doing repairs. 2 questions. A, what is the acceleration due to the tractor beam force? And part B, how far away is the ship if the total trip took 10 seconds? So there's 2 angles here, because the first part of it is talking about forces, and the second part is talking about how far did it move. So that's more of like the equations of motion we learned before in physics. So what we need to do first, before we do anything else, is we need to draw a picture, right? Now, my picture is going to be terrible, right? But this is a space probe, right? This is a spaceship, space probe, right? Something like this, draw a little like, something like that, right? And there's some like alien over here, and basically they're pulling on this thing, and we know that the space probe has a mass of 32.50 kilograms. And it says it's being subjected to a tractor beam, which means some kind of outside force pulling on it, right? We don't even have to draw what's pulling on it, but we have some force here pulling on it, and this force is equal to 140.0 newtons, right? And part A, we need to focus on first. What is the acceleration due to the tractor beam force? So literally, like I said, you can solve most problems in physics with Newton's second law of motion. And now you should by now know that its force is equal to mass times acceleration. And you should put the vector arrowheads, which just means the force and the acceleration are in the same direction, which just means that if I'm pulling on it with this force, then there has to be an acceleration in the direction of the pull, right? And so what do? We're trying to figure out what this acceleration is. Now you can put the numbers in and then solve, or you could just flip it around and say that the acceleration is going to be equal to the force divided by the mass. Take the force, divide by the mass. That's what the acceleration is, right? And the force is 140 newtons. You always want your forces in newtons and your masses in kilograms, and the mass is already given in kilograms, 32.50 kilograms. And so whenever you run this through a calculator, when you say 140 divided by 32.5, you get 4.31. And what units is it? Well, you always want to have your forces in newtons. You want to have your masses in kilograms. And when this happens, then meters per second, meters per second squared is what the acceleration is. So you see what you've done is you've sort of translated the force into a movement, into acceleration. And they're in the same direction, and the mass of the ship, which is, this is the mass, is acting almost like a conversion factor, like from inches to feet or from miles to whatever. It's acting almost as a conversion factor. How much force gives you how much acceleration? How does force translate into motion of the object? That's what I mean by I say it translates it into motion or acts almost like a conversion factor. Now, the second part of the problem says, how far away is the ship if the trip took 10 seconds? So that's a little bit of a tricky question, because you're thinking, what are you talking about? What do you mean how far away it is? Well, what we're saying is now we know that the ship started at rest. The problem said the ship started at rest. So this is like t is equal to 0, right? And so it started at rest, the velocity was equal to 0, right? But then later on down the road, it's over here. It moved. Why? Because we know we're pulling on it with a force. We can erase the forces from the picture. We know the acceleration is now 4.31 meters per second squared. We now know this. And so we know it's going to move because the force is kind of translating the position. It's making the position of the thing change because we're now accelerating the object, so it has to start moving. Now it's some distance away over here at a time of 10 seconds. Because the problem says, how far away is the ship if the total trip took 10 seconds? So what we're really trying to figure out is, what is this distance? And so we're going to call this distance delta x. Right? Because when you have an initial time and some final time and some movement, there has to be some distance it traveled. Now, how do we do that? Because now we're talking about distances, but then you got to remember, see, this is how physics works. You really can't forget the earlier stuff. Now we have to go back to our equations of motion. The equations of motion that we used in the beginning. And one of the main equations of motion was x minus x naught is equal to v naught t plus 1/2 at squared, right? 1/2 t squared. So you can't flush that, right? When you know an object starts with some initial velocity and it's accelerating and you know how long it takes, then you have everything on the right, and what this is another way of saying x minus x naught is another way of saying delta x. So you can just write delta x. What is the initial velocity? Well, it's starting off at 0. So 0 times the total time, this is really a delta t, the total time of the movement there of 10 seconds, right? Plus 1/2, what is the acceleration? 4.31, the units are correct, it's in meters per second squared, 4.31. And what is again, the delta t, the time is 10 squared. So it's 10 squared. So sorry about the collision here on the right-hand side. So what you have is, this is going to become 0. And then you have 1/2 times 4.31 times 10 squared. That's going to be 100 times this times this. You're going to get 215.5 meters. That's the distance traveled, because we're assuming the ship is at rest. We're assuming they're starting at some starting position. How far did the ship move? That's exactly what was asked. It says, how far away is the ship if the total trip took 10 seconds? So you see, we started with a force. We know now Newton's law, so we know how forces produce accelerations. Once we have the acceleration, then we can use the same equations of motion, which we were using in the beginning. We know how long the trip was, the acceleration that was happening, and there was no initial velocity. How far did the thing move? And so now we're bridging the gap between forces, which really cause accelerations, and the actual motion and how far things travel. So as I said in the beginning, this literally is one of the most important lessons in all of physics, because we're going to use Newton's laws constantly. Like literally constantly. When we're talking about waves and thermodynamics and electricity and magnetism, we're still going to talk about Newton's laws, because anytime something's moving that has a mass, Newton's law comes into play. Forces are involved in almost everything in physics, and so Newton's laws come into play. So the main thing for you to understand is F equals ma is a vector equation. Of course, the numbers multiply to give us the force, but the directions of the acceleration and the force, they have to be the same direction. And so I drew pictures to kind of show you that. Here were some simple pictures. X direction force, X direction acceleration. Y direction force produce Y direction acceleration. Some oblique force produces some oblique acceleration, like this. So you can write the vector form of Newton's laws, or you could write them in component form as we have done here, which is what we do in a lot of problems, breaking it up into X and Y directions. If you have multiple forces acting on the object, first you add the vectors to get a single force. We call that the net force, or the sum of the forces, and that's equal to mass times acceleration. These pictures are just showing how the acceleration actually happens, and we went through that. And then, of course, we had the definition of the Newton. The Newton of a force is basically the amount of force required to move a 1 kilogram mass in an acceleration of 1 meters per second squared. Then we solved our problem. Go through this a few times, please. And then follow me on to the next lesson. We're going to solve several more problems involving Newton's second law of motion.